in exploring this responsible AI in area of explainable AI. So last time we have already you have seen what we talk about on explainable AI, where we basically talk about interpretable AI. We talk about the inherent, where you use things like models that are actually interpretable. They come in with an inbuilt system, like the we talk about the things like regression, logistic regression, decision tree kind of model. That this kind of systems or models, they actually come with interpretation that is inherent inside them. You could easily just look at them and know that this is what they are doing. They don't really need a post-hoc model interpretation. But then there is this other models that we need to build a way of surrogate to be able to help us to explain or interpret what the model have done. So it is in that kind of light that we looked at the post-hoc model explanation approaches or interpretability approaches. Although there is this argument in the expert community about the difference between interpretability and explainability, where you see arguments that interpretability is not the same as explainability. If you may ask me, I would say people use it interchangeable, but they are not the same in some certain degree. Because when we talk about explainable AI, explainable AI is a very big word, because to me, it's like an umbrella word in which interpretability is also docile inside. Well, now, why did I say so? Because interpretability itself does not really reflect a human usability of that particular explanation. So the fact that we have a logistic regression or a linear regression model, even if I run an analysis and I get an output or equation, the question is, so what? I will need to interpret it to my audience who are not familiar with these things in such a way that they will be able to understand. So the human explanation is what brings makes the interpretability to make sense. So interpretability, explainability can be used interchangeable, but that does not necessarily they are the same. The fact that you could be able to explain what the interpretable model have unraveled, that's what the explainability is. So the human in the loop or human-centric explanation makes sense when you begin to talk about explainable AI, because the explainable AI again itself would not make sense if you don't explain it to such a way that your audience or your target audience will be able to understand it, such that, like I said in one of my books that I wrote, that explain AI to me like I'm five. It's not everybody that when you come and tell them about AI, they see it as a big buzzword. So if you want to explain it, you need to reduce it to such a level that you could be able to tell them that, oh, just like how you're able to do some sort of computing games that you play. You need to reduce it to such a way they could understand that, oh, this AI is actually helping me to be able to do things that I used to do, but in doing it in a very faster, time-saving way and all that. So you need to find a way to explain it to a layman that he'll be able to understand what you are trying to communicate. Okay, so we will continue again, like I said, looking at this part, but in this case, we are going to look at the breast cancer data set. And remember, the objective is to understand and also to build interpretable machine learning that will help us to classify the breast cancer into benign or into malignant. Also, that's cancerous and non-cancerous. So to gain practical understanding of how this explanation works, if you remember in the previous classes, I treat like a sharp. After I finished the model, then I told you, I said, okay, this is sharp, and then this is line. But this time around, I want to introduce you to something quite interesting and also very nice. I used that in my PhD work, and even the app I developed in my PhD work, I think I used that instead of building separate sharp. I'll talk about the explainer dashboard, and then we could see how it works, and then you could have this takeaway to see if you want to stick with the sharp approach, or you could just put the explainer dashboard. This is a kind of a shiny sort of like an app that you could just build within few lines of code. So quite an interesting thing. And I could see they added one or two features from the time I used it in my PhD work, all thanks to the evolution in AI. But it's very nice thing that you could play around with it after this class. So in order for you to dive in quickly, you will need to install the explainer dashboard if you have not installed. So remember what we say, you use the pep install when you are working on the Jupyter Notebook. And then outside the Jupyter Notebook, you don't need to do the Hyphen stuff. You just need to do the pep install. That's if you are using the CMD interface. So good. But I already have the package installed, so I wouldn't have to do the installation. But briefly, the guy that talks about that originally created this explainer dashboard, probably we could just look at him. I think I did cite him in my work. Explainer dashboard. Yeah, so it's from this guy Ogi or something. I didn't really see him doing much about some stuff. So he did that explainer dashboard sometimes, I think around 5 years ago now. But it's very interesting thing. So it was done by this guy, Ogidiji or something. He should. It's very, very interesting name. So it's this package makes it conveniently to quickly deploy a dashboard web app that explains the working of a machine learning model. So the dashboard provides interactive plots or model performance, feature importance, contribution, the what if analysis, the partial dependence plot, and also the sharp interaction visualization of decision tree, etc. You can be able to explore it on a Jupyter Notebook Colab environment. You can also be able to export it, the result in form of static HTML, ML files. You can also, so he has other beautiful examples like the Titanic dataset and also the documentation. So if you want to read more about it, you could actually see the link, and then you could explore more about this thing. So you could see how it looks, and we're going to see it shortly in action. So quite a very interesting stuff that he did. So having said all that, now let's go back to the Wisconsin breast cancer data set. Now, again, like I always say, the first thing you do is to load all the relevant package. Do not forget, very important, because without the package, you're likely going to have errors. So make sure you load the package. And then remember, this data is a scikit-learn data set. So we already have it in the scikit-learn. So we just need to call the data. But if we don't have the data, then we need to use the read PD read CSV, like and all that. Anyway, so the next thing is you run it, and we already indicate what is our X and what is our Y. I remember we said the X is our independent variables, or Y is the target variable. So again, it makes sense if you make a copy of the data, so you could always go back to see what the data is all about. But we just wanted to combine the target and the dependent variable together. So again, like I said, always check the df.info to see if there are presence of missing values. We can see interestingly, all the independent variables are all floats, although we do have a target variable that is an integer, but that's also quite an interesting. And we do not have any missing value. So you could see all of them are 569 observations. So it did make sense. So again, like I used to say, always try to preview the data, so you could be able to see in sort of what is this data all about, because that gives you like a view, a highlight or something of the data. So you could see it has so many interesting variables that also the ranges are different. Now, one of the things that this preview does for us is that At least from here, I will know if I'm going to standardize or scale my data set or not. But like I said, it's a good practice. Always try to scale your data set. So again, we say we do the df.describe, which gives us help us to see the statistical descriptive statistics like the counts, the mean, standard deviation, the also the 25th, 50th, and 75th percentiles and all that. Now, again, this one, doing this help us to know how distributed the data looks like. Is it skewy? Does it have presence of some sort of outlier? Because if you look at the maximum and also the minimum, you could also look at the mean, then you can have an idea of how the distribution should look like. Now, again, it makes sense. Remember, we are looking at responsible AI. And one of the first thing we talk about is biasness. That model biasness is quite a concern, especially if the positive class is highly underrepresented. Whenever it's underrepresented, you are likely going to have a very big issue. Now, in most real-life application, the classes that you are interested to predict or the positive class is always the rare occurrences. So because they are the rare occurrences, you will struggle with your model. So sometimes, like I say, with all those beautiful AUC you see, it doesn't happen like that in real life. Because if the positive class is very rare, it means that the algorithm doesn't see them often during training. Because it doesn't see them often during training, whenever you are now making prediction, it begins to struggle with it because it hasn't seen them before now. So because it didn't see most of them, is prompt to make errors. And remember what I told you from the onset that AI is data hungry. The more you give him the data, the better it performs. So now see what happens when you now give it very few of the positive instances that you are interested in. And then when you don't have much of these examples for him to see, it begins to struggle when you deploy it in the field. So that's why bias, data bias, or inherent bias or whatsoever that comes with is a challenge. Make sure when you have this kind of thing, you put up measures on how you can mitigate it. Although for this class, I kind of let it slide. And the reason is because we do have a good representation of the benign and also the malignant class. So that's why I kind of say, okay, it's fine, let it slide. But in real life, don't, if it's something that it's going to have effect on your model, then you find a way to deal with it. And there are so many ways we could deal with it. One of the way we could actually deal with that is through, first, we could use resampling approaches. Now, there are several resampling techniques such as undersampling, oversampling, and also synthetic sampling. Probably I will find time before we move to the more complex parts to just talk about them in brief, and then we see how it works. But I'm not really a fan of sampling, and I'll tell you why. One of the reasons why I'm not really a fan of this resampling techniques is because they create sort of synthetic data, to be able to augment what is not there. Now, the creation of this synthetic data on its own, for me, it has created a bias. And I also feel because the real world, the samples that I'm very interested in, they are highly rare occurrences. If I showed the model, I train it to know life is very easy, just like what Nigerians are passing through right now, the fuel subsidy thing. Before now, they could just go to the filling station, get the fuel maybe at the rate of 200 naira. And then now the president came up and said fuel subsidy is gone. Now people begin to their life was just turned upside down in one day. And then they begin to struggle because there was no preparation that was put on ground. That's also what happens when you deploy your model into the field, you train it on this synthetic data, which is the fuel subsidy, and then when you go to the field, you remove the subsidy. See, the model will struggle because it was trained to believe that the rare and occurrences are always going to be happening frequently. And then when it goes to the field, they are not. They are rare occurrences. And then it begins to messed up because it haven't seen it wasn't used to that. So I was of this opinion that instead of that, let me train the model the hard way. let me tell the model right from training that this is what you are up for. This is what you're going to face. You could imagine maybe if Nigerians were trained from the onset that there is nothing like subsidy, Nigerians could have somehow adjusted and they could have known that, okay, this thing don't even exist. Our government are not subsidizing anything for us. So we will survive. Like somebody that finds himself in the Western world here, you already know that, okay, if you are an immigrant, you are not yet their citizen, you do not have entitlement to certain benefits. So you have already customized it in your head that look, you just have to survive on what you have and all that. So you make your budget based on what you are getting, you know. So, but on the other hand, when you have this whole expectations, and then when those things are not there, you begin to see that you know you struggle and your life you couldn't cope. You see a lot of things and all that. So that's my own kind of approach. That if you train the model looking for a way that the model could be able to use what it has to learn patterns that even when it goes to the field, it will go to the field with the patterns it has learned. I feel it's quite far much better than for me to begin to train the model on palliative or on subsidy. And then when it goes to the field, these things are not there and then it crashes. So, but it's my personal opinion, of course. So that doesn't connote everyone's opinion in the field. So again, like I said, we did have a good representation of the both class, although we could see to some certain extent that this class happens to be more than this class. But again, if you are a good, you know, so like I said, another very important thing for us to do is to create these bivariate visuals. And example of the bivariate visuals is the heat map of correlation between the variables. But again, you know, you don't need the target variable because that's the variable that all the other variables need to compete. Instead, in the bivariate plot, what you are interested in to figure out is are there competition among the variables themselves that has the ability to slow down the performance when they are working in predicting the target variables. So that's why we always try to do this variable. And like I said, if you have lots of variables, you don't need to visualize it. You could visualize maybe the first 10 or 20, and then you could output the result in form of a CSV file. Then from there, you could check, and then you see some of the variables and see which of them are having issues around multicollinearity and so on and so forth. Anyway, we can see some of them had this multicollinearity happening, but I think in the last class I told you guys why and why this is not really an issue because of the source where these things were measured from. So because of that, we should expect that high level of collinearity between them. But anyways, this doesn't stop us from saying we should use or drop. So if it's a feature selection task where we highly need to prioritize, for example, if we need to get the best features that we need to evaluate or test them in the lab, we do not have the resources to measure all these features. So because of that, we want to prioritize only the features that are much important to us. So because of that, we will need to introduce a feature selection approach. And in the feature selection approach, we will now be able to explore all these methods we have looked in the previous classes, where we now be able to come up with the best feature subset. Then we use them for the supervised learning phase. Now, the next thing we need to do, so good. So we had a kind of an overview of that. I thought I asked it to drop. Well, anyway, so we do have an overview of the performance, and then next thing we are going to do is fair representation of classes. Okay, yeah, we have seen that. But again, because of the fact that we did have some sort of underrepresentation of the benign class, one of the things we need to do is to encourage, if we want to mitigate the issues around the biases, one of the way we could mitigate it is by using stratification. Now, what the stratification is going to help us is it will preserve the original structure that is in the universal set. So if we are using cross-validation to split the data set into training, testing, because what the cross-validation does is that it splits the data set into training and testing, Then we could tell it we need 5 in 5 places. So it means that the training and testing in the first phase, I don't know if I could actually make a sketch. Well, I don't have a board. I could have shown you guys how the cross validation looks like. Anyway, I think I could get a figure of it. Cross validation, stratified. Yeah, I think we can have an image of good. Yeah, I think this is a good way to represent. Good. So what the, I don't know if you could see this image. Can you see the image? Can you see this?
Yes.
Oh, great. So you could see at the first so if we said 5-fold cross validation, what it means is that we tell the data to take all the set, split it into training, testing, training like that. Then the last split or the first split becomes our testing. So we will have 1, 2, 3, 4. The 4 of them will be trained set. Then it will use the last one to become testing. Then if we are iterating the second time, it will move, the testing will move to this one, and these other ones will be training. When we move to the third one, it shift again. If we move to the fourth one, it shift again. Then if we move to the fifth one, it shift to the last one. So this way, it will take in all the 5 iteration, we will get a testing, which was a training in the previous iteration. So that's how it does. But interestingly, in the Stratified, it will preserve the original structure of the data. So you can see we still have this, we maintain this original structure. You can see this is the class distribution, right? And you could see in all the split, it maintained that same structure. So that way, no split will go without having a touch of the rare classes that are occurring. I don't know if you guys understand with me my point. This is an imbalanced data set because this male are more than the female. Now, one way to mitigate the bias, and we don't want to use resampling because, like I said, the resampling, if we are using oversampling, it means we create synthetic data to fill up this so both of them will be equal. If we are using undersampling, it means we will reduce this so it will come back to this level. So you see, we are going to lose a lot of information if we are using undersampling. If we are using oversampling, we have to generate synthetic data to fill in this gap. And then if we are using the smooth approach, which will combine the both kind of approach, it's going to also generate synthetic data for us. And again, like I said, we are creating information that are not true, that are not there. So instead, we will say preserve the original structure of the data. But in this case, for example, we say 5-fold. We want 5-fold. So each of the fold that you are going to create, you will preserve the original class distribution structure. So that way, all of them will have a test. A good example is the pot of soup. The first one, I still like the food one. I think it's a good example. If you look at the pot of soup, if you take 5 plates from the soup and you fetch the soup in all of them, everybody will have the taste of the original soup that is in the pot. Do you understand the logic? You will have a good taste of the soup because it's coming from the soup itself. So everybody that tasted is the same. The same thing if you have a mango and you slide the mango into 5 pieces. No, I think the mango example will not be true because there are some part of mango that is very sweet compared to the other part. Especially, I think the thick part of the mango is not as sweet as the other part. So I think the mango example is biased. The soup example is better. So in the soup example, all the plates that you fish the soup, they will all have the taste of the soup. But if we are looking at it in another way, maybe in form of the ingredients that are there, maybe meat or fish, there is high probability that some plates will have more meat than others. So I would not use the content, but I'm using the taste of the soup. So when you're looking at the taste of the soup, all of them will have the same taste because it's coming from the same source. Okay. So that's what the stratification does. It will preserve the original this class distribution, but again, it will help us not to have a particular fold that is not having anything. Because if we do not use the stratify, we just use the cross validation, there is that high tendency that one of this class will not have any representation of this. It will be just all of this, and there will be none of this in it. So you will see it having this ratio. Anyway, let's see what happens. So we are going to use the stratification for here. You see, we use the stratify k-fold 5 splits, and then we ask it to shuffle it through. So it means that at each shuffle, this is what happens. So each of the shuffle, we are going to have, so this one that was a testing, when we say shuffled, it's become a training in the next iteration. It becomes the testing here becomes a training in the next, and then we create a new test like that. So you tell it that at each time that it takes the stratified from the data, it should make sure it returns back to shuffle it. So it means we are sampling with replacement, in other words. Okay, so and then the random state, of course, we could set the seed to any number we want, and then most importantly, so what we are trying to achieve here is to mitigate that bias that I told you guys in the data set. Remember, in this place, we talk about that this bias is quite a very big issue. This bias and discrimination, it creates systems that doesn't represent everyone. And because it doesn't represent everyone, it could be a very big issue. So, for example, in the case of this cancer that we are looking, imagine if there are very minute number of Black people in that set, they will end up not being equally represented. And then when the system is deployed, it will definitely misclassify them. So doing it this way help us to keep it. So what we are doing here was to train the model on a future important classifier as sort of a future selection, so that we are going to, at the end of the day, select only the ones that has consistent future support across the 5-fold. So remember, already from here, we did have some issues of collinearity, but most importantly, because we want the future that equally represent all the interests of everyone in the society that we want to create. So if we looked at the future that has the property of everyone, it makes sense because it means we are able to deal with an issue called, for example, sparsity. Secondly, we are able to focus our attention on building an inclusive sort of society. So that's what we are doing. So we stratify, and then we train the 5 folds that we stratify with a random forest, and we create a future important CSV file that has future importance from the first fold, second fold, down to the 5th fold. And then we now look at the futures that are consistent, and the ones that are not, we forget about it. It means those futures actually do not have the inclusivity of everyone. So that's what this part of the model is doing. So we use the random forest to do that, and then we filter. So now it has run, and now it has returned the future importance for each of them. And you could see this is the future importance score for all the folds. So the next thing we are going to do, we are going to look at the futures that it selected that has consistent across the fold. So now let's look at it. This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31. So I think all the futures, if I'm not mistaken, all the futures are being represented. So we do not have anyone that don't have any future, because we asked it here to select the consistent futures that have non-zero future importance. So that's what we did here. So that's why we say future importance greater than 0. So select all the ones that has this consistent future importance. So now we are going to take that consistent futures that we have, we are going to apply it to the training and testing. That because now we want to train the final model, but we want to train it on only the reduced subset that we have. Although in this example, we see almost everything has been included, but I guess if you're using a practical example of another particular area, you may not have all the futures equally represented. So what we are now doing is we take this consistent future from here, we apply it to the original X or independent variable to extract only the futures that has that consistent future importance from the first phase. So the random forest here was not acting as a classifier algorithm that we wanted to use for a prediction purpose. It was only acting as a filtering algorithm that we need for a future selection. And remember, we talk about the different future selections we have. We talk about the wrapper method, the filter method, the embedding method. And remember, the random forest fall under what? The embedding method. So, yeah, is it embedding or also? Yeah, embedding, not wrapper. Because wrapping method has to do this recursive. So it falls under that. So the next thing we need to now do is to perform this next phase to split the future into training testing. So we are setting aside 20% for testing, and we are taking 80% for training. You could still see we use the stratify equal to y to maintain that same structure like I told you, because remember, we want to mitigate the model biasness so we don't have issues around it. So again, when you run it, you have this. Now, the next phase we are going to do is that we want to train the random forest and XGBoost model. And remember, prior to training, I always used to say we are going to use the grid search. So these are the grid search model parameters that we have indicated, and then we will take the best performing parameters and use them subsequently for prediction. So now what we are doing, we are training the random forest, and then we're also training the XGBoost. So this could take a bit of time, but again, of course, we know we're not having much depth. I think it's just 5, 3, 4, 5, and none. And yeah, so we are done with that. So we could see that the best performing score from the best parameters we have is around 95 points. Let's say 96, both XGBoost and random forest. So the next thing we need is to make prediction on the target on the testing set. So which, remember, the 20% we set aside. So now this is the prediction we have made. So now let's look at the classification report. So when in the classification report, you can actually see the precision for the benign is 95, 93, 94, and it has 42 support. And the malignant is 96, 97, 97. Now, one thing I want you to take note is you can see the malignant has this high score because remember it is the dominant class. It was the dominant here. So you could see, that's why I told you the more the AI sees it, the better it performs. So the random forest looks fine to me. The XGBoost also look fine. We have 95, 90, 93, and then 95, 97, 96. So it makes sense. So now we want a global explanation using the future importance. So the future importance will give us a global explanation of which features actually is the most important feature. But again, we are restricting it to only 10. In some cases, we can ask for 15. It depends, all depends. But 10 is also fine. So yeah, so if you ask for 15 features to give you, you will see that the worst parameter according to random forest. So this feature importance is coming for random forest, okay? And we could see the worst parameter is the most important, and the least one is the mean texture. Again, remember the font size, okay? We make sure the font size is around quite big, because like I told you, if you are making publication standard, always take note of that so that your reviewers will not have to shrink their eyes. Then also, again, last time I talked about the graphics, that make sure when you are saving this plot, save them as in a very high graphical format. Someone may ask, what are the high graphical format? The PDF forms, the SVG, SVG, TIFF. Those are high graphic format that, but the PNG, JPEG, with time, their quality reduces. So that's why I don't encourage you to use that. Okay, so the next thing we are going to do is to look at the future importance from XGBoost model. So for XGBoost, we could see worst parameter still looks as the first most important feature. Then worst radius, well, random forest says worst area. Anyway, the least most important is radius error. Random forest said is mean texture. So again, let's look at the AUC analysis for both the random forest. We are going to color the random forest orange and the XGBoost dark red. So again, we almost had a perfect score of 99, 99 for the both of them, which is interesting. But like I said, in real life, you may not have this. You will have something in between. So it may not be that good. Now, all these are interesting explanation, but they are global. They don't really give us this granularity that we need. So we want this sort of a granular explanation where we could say this person, this is his prediction and why. This other person, this is his prediction and why. So such kind of thing means that we need a local explanation. So like I highlighted last time, the explainer dashboard helps with such kind of thing. So if you have installed the explainer dashboard, what we want is for the explainer dashboard to do this explanation for us. So now we are going to restrict it to the best model. So how we select the best model is if the best score of random forest is better than that of XGBoost, then it should be random forest. So, however, we could see that the model detected, I think, XGBoost to be the best model also for it. So we also ran, for you to run the explainer, remember this is a classification problem. So we have classifier explainer. So you wrap it, just like we did in Sharp, you wrap it around the best model. So this is the best model, you wrap it. And remember, we are focusing on the testing, that's the prediction. So this is the test Y and this is the Y test. So the next thing we are going to do is we want to look at the model, but again, if remember, we can visualize the explainer, we can visualize it in our notebook. We can also have like a HTTP link where we could visualize it outside the notebook. So that's what we are doing. So for it to do that, it's to a bit take time to fit because it's fitting for everybody in the testing. But by the time it's finished, you will see it will pops up and give us this dialog that we could be able to see what's happening. So we ask it to run, and then we set a local host of around 127.01, and that's to run it. So always make sure you set the host where it will run. Now let's see what it was able to do for us. It calculated the sharp value. It also calculated the prediction probability for us, the matrix, the confusion matrix, the classification repos, the AUROC curves, the this is precision recall curves. We also have the lift curves, the XGBoost model, the dependency plots, the permutation importance, the prediction percentiles, and so on and so forth. Now, you can see how it looks like. Is it not beautiful? So now you can see the positive class here is malignant, and this is a general, so this is like a global explanation that we showed from the beginning, and you could see it actually ranked them where the worst was 1, the second one was concave, the third one was area, error, and so on. For all the parameters, you can see it actually run it for all the parameters. Very interesting. So the next thing, let's look at the classification report. So this is the classification start. We could also see the cutoff prediction probability. So you could actually slide this around. You could take it to this place if you want. You could take it to this place if you want. So depend on what you want to slide it. But I think the default is 50. You can also see the percentile of the sample. You could play around also with it. Now, interestingly, you can have the model performance in summary here. You can see the accuracy, the precision, the recall, the F1 score, the ROC curve, the precision recall curve, and the log loss. Now, you can also see the confusion matrix. You can see it gives you in percentage, which is interesting because you could see out of the 42 persons that it classified, it actually got 38 of them right, which is around 33.3%. It only missed 4 of them that it misclassified, but which is fine. Then for the malignant, we see we got around 61.4% right out of around 72. It was only 2 persons that we misclassified. All these ones at the diagonals means we got it right. So in total, you can see that the error we have, well, it's not much. It's not actually up to 5%, which is quite interesting. Now, let's also slide down to see another interesting thing. This is the precision plot that we have. Now, we could actually see the percentage of malignant versus the predicted probability. So we could see how it's been counted and how it's been predicted. We can also see the percentage above and below the cutoff. You can see how it makes this prediction for the malignant, and this is for the benign. Interesting. We could also see the AUROC curve. You can see this is 99. The TPR, that's true positive rate is 1.0. False positive rate is 0.1. It means we have a very small false positive rate. And you could also see for the precision recall curve, we also have 1.0 and the precision is 95, the recall is 99. Beautiful. Now, another interesting is the lift curve. So the lift curve helps to show what the perfect model looks like and the model we got and also the random model. So this is the perfect model, which is the blue one. You can see the only place we differ from the perfect model was just around this place. And again, you could actually see that you could see these values. You can play around, you can move around, you can move this dialog. So you can see it's actually interesting. You can also see the cumulative percentage categories of the samples. Now, when you have the X top percentage, it means you can have the first top 5, you can move it to the first top 40 and the first top 60 and so on, depending on what you want, and all that. So now let's look at another another plot we have. Let's look at another interesting thing. Now, this is the individual prediction. So on the side of the individual prediction, now let's pick one person, one sample from it. Now, this sample here, this is let's say this person's ID is 256. So if we pick this person, we are going to see the results of this person. So this person is actually benign. 99%, the model will show that this person is benign. Interesting. And we could see everything around that makes us to know this person should be benign. These are all the classification, the final prediction. So the worst area, the area texture, the radius, the mean area, the mean smoothness, and so on and so forth. You could see what actually contributed for them to say why this person. Now, this is the reasoning behind it. So the contribution table, you can see the average population is 63.31. The concave area is the effect. So we could see all these ones are added to the reason why it classified the person to be that. Then the partial dependency plot for this person as well. You could actually take a look at it and see how these features affect each other, because you could, of course, play around with any of the features you want. You can pick texture to see how does the partial dependency plot for texture for this person look like. Now, let's see another person that will likely be, okay, so this person too is benign. Let's see if we could get somebody that is malignant. So this person is also benign. Okay, let's see. Probably we get someone that's malignant. Let's go. Oh, great. So now we have gotten someone that is malignant. So this person, this sample 537, it classified this person to be malignant with 98.6%. And it was very few percent that was showing 1.4. So again, we can see the features that are contributing. Now you can see the mean smoothness and all that, but we can see the larger contribution is coming from the worst area and followed by I think the worst concave points, then followed by the mean concave. You can actually see how the features are contributing. And then also we could actually see the contribution of each of the features. Again, you can see that the best features was coming from the worst parameter, which is around 86, and then the worst area. Oh no, I think the worst area was actually at the top. That's around 487, which is plus 69 contribution, and this was around 11.82. Interesting. So you could see how it's doing, and then the partial dependency again for all of them. You can see the worst parameter. You could see how the features is playing with the features of how these are distributed. Now let's see what other thing can we look at again from this. What if? So for this person, what if analysis. So the what if analysis, I think the person we're looking at is 537, if I'm not mistaken. 5537 or 537. Okay, see. So you can actually see again, yeah, this person is 99.8% malignant. Now, the what if analysis is just like remember we talk about the adversarial that so it's sort of like if there is a distortion, what happened? Can we still have a robust prediction for this person? So that's what the what if tells us. So it's kind of like a sort of a mini sort of simulation of what if scenario. What happened if this is this and this is that? So you can again see that the partial dependency plot and all those things are still okay for that person. So I could see the concave. So it gives us so many things as well. Then future dependency, again, you could see the future dependency for you can select for everybody. So we can pick for this person 537. Good. So this one is the future dependency plot for 537. You can also see how where that person is in the sharp value. So you could see this is where this person is in the sharp value, and you can see the features that are contributing to that person. Remember, this is the worst concave versus the worst parameter. So you can also as well change other features to see how the texture goes. You could also select for another person, maybe 501. You could also see where this person is located, which is around here. And then you could also see the features that are contributing for that person. So if you pick the 3.6, now this is the detailed. If you want to see the detail, you can also do that. So good, you can also see the detail of the sharp. Remember that sharp plot that I used to show you guys. So it is actually what they were trying to do here. So again, if you want the detail for this person, let's say 501 for their sharp, you would see it could output the sharp for the person, and you could be able to see what is pushing the prediction for that person and what is not pushing the prediction for that person. So it could give us for everyone. And then you could also look at the depths of the, let's say 3. It gives you the top 3. If you say you are looking at the top 6, it will give you the top 6 for that. So you could see how interesting this could be. And again, we could also look at the decision tree for this person. Let's pick one person here. You could see what happened. Let's say we want the 3 to be just 3. Good. So this could also tell us how the 3 of prediction of that person looks like. And again, we could do for another person here. We could show us if we pick the depthness of the 3 to be 2. We could also be able to see the graph, generate the 3 graph. It should be able to, if I'm not mistaken. Okay. So I think we needed to install the graphite or something. I don't know if I did the installation of the graphite, so I guess that's why it didn't generate the 3. But again, it could have generated the 3 for us to see how we do the, okay, let me see if we can do the installation of the graphite. App installed. Let's see. Let me see. I do that correctly. So we could be able to see the tree. Okay, I think the graph is satisfied. So why? Anyway, I don't know why we couldn't get the tree for this, but I remember I did visual. Okay, yeah, good. So we did have the 3. So you can see for this person, you can see how the decision tree for the person looks like. So you can see how is splitting. This is quite very, very interesting. You could see what are contributing to the prediction from the decision node to the different splits. You could actually see what if. So if we restrict the 3 to just depthness of 3, again, we could generate. So you could see just 3. You can see for another person. Good. So you could see this is for different persons. This person was malignant, benign, malignant, benign, malignant, benign, like that. Let's see another person. So you can also see this is for another person. So as you play around, you consider to see different. So if you increase the depthness, it will change. So you could check for each different people. You could play around with them. So you see, so the more you change it, the more you could see for each of them. So quite interesting stuffs that are really there. So I think that's all. Benign. So you could also check for the benign class as well to see what is happening. So depend on which of them you want to. So you could also see everything. So you could see then if you want to download, you could download all the tab, depending on what you want to download. So again, you can download it as a static. Let's see what happens if we download everything. Let me see. Okay. So yeah, so you can download let's see. Okay, good. So the download is complete. So again, you can see, but the download is not going to be moving again. I don't know if you get the point. So you see the download won't move because it's just going to be static, like that. And from here, you can decide to save it as sort of PDF or something. You can save depending on what you want to use. So this is how the explainable dashboard works. So you can as well apply it to any other thing you're using, depending on the kind of model that you are training. So I think with this, I have